All right, so now we're going to go on to talk about the false discovery rate. And it turns out that this fun data set in the ISLR2 package has not just 5 managers, but actually 2,000 managers. So we're going to load them all in. Gareth is going to do the honors here.
I'm going to do the work.
It's his computer. As you all know, I don't work with PCs, so I really don't have a choice. Okay, so we read this in. And now for each of these 2,000 managers, we're going to compute the p-value. Okay, done. And now it turns out that we can use the same p.adjust function to adjust those p-values using Benjamini-Hochberg. In other words, to compute what is sometimes known as a q-value instead of a p-value. So if we do that here, we see that for the first 10 managers, the first manager's q-value is 0.089, the second fund manager's q-value is 0.99, and so on. So we can think about this as telling us like the threshold for FDR control at which we would be rejecting any one of these particular fund managers. So for example, if we wanted to use an FDR threshold of 0.1, then we would be rejecting the null hypothesis for any fund manager that has a Q value below 0.1. So we would reject, like for the first one, because its Q value was 0.08989, and also for the, let's see, the sixth one, because the Q value was 0.075, but not for the second, third, fourth, or fifth ones.
And in total here, out of those 2,000 fund managers, 146 ended up with a Q value below 10%.
So how do we interpret this Q value below 10%? This is saying, okay, well, this is saying I want to reject the null hypothesis for any fund manager corresponding to an FDR or a Q value below 10%. So that's saying that I basically want a list of fund managers for whom I'm fairly confident that most of them really are getting non-zero excess return. Did I get that wording right?
Yes, yeah, you're learning.
Thank you. I'm a really fast learner. So we're trying to reject the null hypothesis for any fund manager where I'm fairly confident that the excess return is non-zero. And in particular, if I'm rejecting the null hypothesis for a fund manager, I want to know that not more than 10% of those fund managers for which I'm rejecting the null hypothesis are actually false positives. So to try to say that a little bit more simply, if I give you a list of fund managers where I say, I'm fairly certain that these are the ones who have non-zero excess returns, I want no more than 10% of those to be false positives. That's what it means to be controlling the false discovery rate at level 10%. And there's 146 such fund managers, where probably out of these 146, around 14.6 or maybe 15 of them are actually false positives. But most of them, I can be fairly confident, have really non-zero excess return.
Yep, exactly. Okay. So if we look at the Bonferroni Cutoff,
bad news bears.
We wouldn't have picked any of these fund managers using this is using the 10% cutoff here.
So if we use Bonferroni to control the family-wise error rate at 10%.
We couldn't reject any of these 2,000.
And of course, family-wise error rate and false discovery rate are really telling us two different things. Family-wise error rate is saying, I don't want to falsely reject any null hypothesis corresponding to a fund manager. I don't want more than a 10% chance of any false rejection. That's just a really, really
It's an unrealistic.
Bar. It's unrealistic, yeah.
It's unreasonable.
Whereas FDR is saying, okay, I want no more than 10% of them to be false positives. All right. So we had just shown you how to perform Benjamini-Hochberg using the p.adjust function. And that is a really good strategy if you want to live an easy life where you just let R do the work for you. But if you want to really roll up your sleeves, I don't have sleeves to roll up, but Gareth does. If you want to roll up your sleeves and do the work yourself instead of relying on p.adjust, you can actually implement Benjamini-Hochberg yourself. That's what we're doing now. First of all, we sorted the p-values. Then we are having m be the number of p-values. In this case, that's 2,000. We're setting q to be 0.1 because that's the FDR threshold that we want to use. And now what we're doing is we're creating this object called wh.ps, which stands for which.ps. And that's going to contain the indices of the p-values that are less than q times 1 to m divided by m. So what's going on here? Well, p's is this object that contains the sorted p-values. And wh.ps is going to contain the indices of the sorted p-values where like the jth smallest p-value is less than q times j over m.
So basically below that red line that you had in your plot that you showed earlier.
Exactly. So like for the first smallest p-value, wh.ps is going to contain the number 1, if the first smallest p-value is less than q over m, and it'll contain the number 2 if the second smallest p-value is less than 2 times q over m, and so on.
Okay.
And now we are going to just store the largest of those wh.p's, because I want to know the largest p-value index that was part of that wh.p's object. And if the wh.p's object is just empty, I just want wh to not throw an error, which is why there's this this if-else statement here.
Okay, so let's do some plots. So this is just plotting the p-values sorted, right, from smallest to largest.
Yeah, these are the sorted p-values. Again, my y-axis shows the p-values on the log scale. Actually, the x-axis is also on the log scale. This is a log-log plot.
Okay, and
now we've colored in blue the p-values that are less than the
Benjamin-Hochberg cutoff, right?
Yeah, the ones that are below the Benjamin-Hochberg cutoff.
Below, well, that at least are less than the last one that's below.
Right. So remember, my wh.p's object tells me which of the p-values falls below the red line. So wh.p's tells me which p-values fall below the red line, and then wh tells me the largest of the p-values that falls below the red line. And that's like the rightmost blue one is the largest. And so everything smaller than that largest one I've colored in blue, because those are the null hypotheses that we're going to reject at a Benjamin-Hochberg FDR cutoff of 10%.
And these are the 146.
Yep, there's 146 of them, exactly.
And then the green line
is no bueno. That's the Bonferroni threshold, again at 10%. And we can see we didn't manage to reject because that involves like 0.1 divided by 2,000. That's just too much to ask of our poor p-values.
Okay. All right. So that's the manual way of doing it, or you can use the automated approach.
Which is the p.adjust function with method equals bh.
Yep. So
So
the resampling approach.
Resampling, yeah, this is the fun part. Well, I know it's all been fun, but now we're going to attach this con data set, which is this gene expression data set. And it consists of a training set and a test set. But for this particular analysis, we don't need that division into a training and a test set. So we're just going to smoosh them together using the rbind function. If you're not familiar with rbind, it just creates a big matrix by binding together the rows
of two matrices.
Yeah. And then we're also going to create a y vector, which just is going to tell us which class an observation is in. We have to combine y train and y test, again, because we don't care about the training versus test set distinction here.
And so we end up with a matrix of 83 rows and 2,308 columns.
So each column here represents a gene.
Okay, and we're going to do a hypothesis test.
What does each row represent, Gareth?
Each row represents
an observation.
An observation
like
of a patient
sample.
or, yeah, exactly. And so we're going to perform 2,308 hypothesis tests here.
Okay. So here we can see that there's actually 4 classes, classes 1, 2, 3, and 4. But to make things easy here, we're actually just going to compare 2 of the classes. We're going to have a comparison between the observations in class 2 and the observations in class 4. So all that we've done here is we've set the data matrix X to contain X1, which is the observations in the second class, and X2, which is the observations in the fourth class. There's N1 observations in X1, and there's N2 observations in X2.
So N1 here and N2.
Okay, so 29 observations in X1 and 25 observations in X2. All right, and now we can conduct a t-test on, let's say, the 11th gene. This is a 2-sample t-test. You can notice this argument that says var.equal equals true. So there are like a million flavors out there of 2-sample t-tests, all of which make slightly different assumptions. And this is just like a super plain vanilla one where we're assuming that the variance in each of the 2 classes is the same. It's not terribly important. And if we compute this t-test on the 11th gene, we get a t-statistic of negative 2.09, which corresponds to a p-value that's 0.04119.
But this p-value is calculated under the assumption of a t-distribution.
That's right, which is basically very similar to a normal distribution. It's just an assumption that it's using the theoretical null distribution for t. So basically, under the null hypothesis, we're using the fact that this test statistic should have a t-distribution with, 29 plus 25 minus 2, so 52 degrees of freedom. And a t-distribution with 52 degrees of freedom is basically indistinguishable from a normal 0, 1.
Right.
So this p-value is under the theoretical null distribution.
But we had to make a few assumptions to get to here. So now we can use resampling approach to see if that seems reasonable.
Yeah, let's do it.
So we'll set the seed equal to 1 so the results are reproducible. And we're doing the non-lazy approach
I'm
here.
not lazy right now, so we're going to have a big value of b. We're going to sort of reshuffle our data 10,000 times. We're going to have TBs be a vector. So TBs is a vector containing the test statistics for our reshuffle data. First, we're going to set TBs equal to NA. That's just like a convenient thing to just set the elements of a vector to while we are waiting to update it. So first, we initialize TBs to just be a vector of NAs. And then for b from 1 to capital B, which is 10,000, the first thing that we do is we create what we're calling DAT, and that's just like a reshuffled version of the 11th gene using the sample function, which just reorders the elements of a vector at random. And then we're going to compute on that reshuffled data the test statistic, that 2-sample t-test again, where this time we've just taken the reshuffled data and we've taken the first N1 observations, and we're thinking about that as our x1, and then the remaining N2 observations, we're thinking about that as our x2.
And you saw that loop took less than a second to compute. So for a simple calculation like this, even 10,000 doesn't require a lot of energy. So what does this tell us?
Well, what we found is that, remember, our true test statistic, it was around -2, I think, and that was called TT. And the empirical, or the resampling null distribution that we got for the test statistic is the TBs. And we found that only 4.16% of the TBs are as large in absolute value as the test statistic for our true data.
Which almost perfectly matches the theoretical p-value we got previously of 0.04119, this value here.
So what this means is that our resampling p-value is 0.0416. The theoretical p-value is 0.04119. All's well in the world. In this particular instance, it didn't really matter whether or not we used resampling to obtain our p-value. But if we feel nervous about the assumptions that went into that theoretical p-value, then we can be happy to know that our resampling p-value made fewer distributional assumptions. Gareth sort of jumped ahead here, but what we can see here is this figure showing in orange that theoretical null distribution, which was, again, a t distribution with 52 degrees of freedom, which is basically the same as a normal 0-1 distribution. And then the resampling null distribution, which is the yellow histogram, they really are almost identical. The blue line is the observed test statistic of -2.09. And it should be no surprise that based on how similar the yellow histogram is to the orange theoretical null distribution, it should be no surprise that the theoretical p-value and the resampling p-value in this case are basically identical.
Just reconfirms that it's reasonable to use the t-distribution here.
Right.
Okay.
So I think that's it. There are a couple topics in the lab, in the textbook, that we haven't covered today. One of them is Tukey's test. Is that right? Was it Tukey's? Yeah.
Tukey's method.
Which is sort of a specialized approach for controlling family-wise error rate in a very particular setting.
And we also skipped some of the latter material in the chapter on doing resampling with FD.
Resampling to compute false discovery rate.
Right.
So yeah, check it out on your own, and thanks so much. This was
has
fun.
been fun.
Yeah, we'll
Yeah,
see if
thank you.
Gareth and I are still on speaking terms when the cameras turn off.
Yeah, you won't know, but
I'm optimistic.
yeah.